if there's something off in the distance and we can't get to it in the map, we need to be able to find that measurement using another method. And the method I propose is, again, using our fantastic angles. So, what you do is you'd say my error is going to be plus or minus whatever half of my lowest resolution is, right? Because you're measuring to a marker, but it's never going to be exactly on that marker, right? It's going to be closer to that marker than either the next marker or the previous marker. But, you know, our eyes can deceive us. That might not be true, and the error that you introduce into the system is, you know, that plus or minus 0.4, basically, where you can tell how close it is to something, but you're not going to actually, you know, mark a 0.3 if you're saying it's 1 millimeter. You're not going to say it's 0.3 millimeters. It's either 0 or it's 1. But in reality, it's probably 0.3. But you can't say that because you don't actually have a measuring tool for 0.3. And we're back. And this time, I have a tape measure. Now, what are we going to do with this? Well, what we're going to do with this tape measure is we are going to measure two things. We're going to measure the distance between two markers on our map here. We're going to be using metric, of course, because who uses imperial? Americans. Americans use imperial. I'm an American. And in fact, at my job, I use imperial, and it is the worst thing in the world, so why would I use it in my free time? All right, that is 4.5 centimeters. So 4.5 centimeters. Let's write that down. Got to keep those good notes. So if I divide 4.5 divided by 3 millimeters, which centimeters and millimeters, does anyone know the conversion? Centi means 100, milli means 1,000. So a centimeter is a hundredth of a meter, and a millimeter is a thousandth of a meter. So if you divide 100 divided by 1,000, you get 1/10, which means that a millimeter is a tenth of a centimeter. So if I want to convert that to a centimeter, I'd move the decimal point over 1. So that's 0.3. So 4.5 divided by 0.3. And that becomes... That seems all fine and dandy. But there's an issue, right? I don't know any of the angles of this thing, right? I don't know any of them. How could I possibly claim to find them? Well, I can tell you this. What is this triangle right here? It's a right triangle, right? Which means that this length right here, z squared is equal to y squared plus x squared because of the Pythagorean theorem, right? Good old Pythagoras giving us some good details, which hopefully I'll be able to illustrate in a second. I just have to give it a good think because I forgot my paper that I wrote this down. And without my paper, I am useless. I need my notes. Or it's going to be you and me thinking. But I do think it's important to show how much, you know, you have to think about things like this, because so many people get discouraged because they, I don't know, see your teacher and you're like, man, the teacher just wrote down on the board, he knows how to do it. It's like, not really. Like, man, I learned this stuff too. I learned this stuff a while ago. Hell, I was in high school and did all that stuff, but it still takes me a good while to think about these things, and maybe I'm just slow, but, you know, I think even if you're slow, you can accomplish great things. So, let's give it a good think. And what else do we need in order to figure this out? We're measuring tau. And actually, we're not... Well, yeah, we won't measure theta. Actually, we'll will derive theta, just because the more things you measure, the more error you introduce into your, the more possibility for error. So, and that's also me saying that I think we can measure rolls a lot more accurately than we can measure, like our roll is with plus or minus a single arrow, but our angle measurements can be plus or minus up to 10 or something. So we definitely want to focus on the accurate measurement, the more accurate measurements we have. And they have that freaking water purifier thing. I don't know if we have water purifiers that, you know, exist based off of plants. It's pretty neat. So we have our length calculator. It calculates length. That's why I named it the length calculator. We're almost there. Currently t is negative. Pay no attention to the negative behind the curtain. We need to measure theta 2. And theta 2 is going to be this degree, this thingy, this angle right here. This doesn't make a whole lot of sense to me. Huh. What's going on here? Well, because, I mean, the reason it doesn't make sense is because this says it's 5 arrows away. I don't know about you, but that doesn't look like 5 arrows. So where did we go wrong? Where did we screw up? Where did we mess up? Tis an issue. Indeed. Ooh. That's kind of unacceptable. That's in the range of, this might be useless. Yeah. Yeah, unless we can get our angle measurements a lot more accurate, I don't think we can. I mean, I can't justify 100 arrows of error when the total distance is probably 100 arrows away. You know, we're talking about like 200% error on a measurement. And that's just something that can't function. Oh boy. Eventually the light will come and visit us. We're also hungry and thirsty, so I will eat something and I'll go to our water purifier and go ahead and drink something, because you gotta take care of yourself, you know? Now, let us talk about error. So sure, we can say x1 is a number plus or minus blank, and x2 is a number plus or minus blank. But we don't know what our rhombus is, right? That's going to be something I'll talk about soon. And then, but how do we translate that into, you know, our error for our z1 and our z2, which is eventually our height, right? Like, and our phi right here, right? How do we get how are we going to measure an error when it goes through this complicated tangent function, right? We don't know what happens to the error when that happens, right? So let's go over some simple examples of error, and hopefully this will help us to better understand the more complex aspects of error. If I draw this arrow up here, we will need to be able to, so that's why we multiply the error times 2, right? Because this will translate to our 2 times x low equals, or 2 times x, I should say, equals our 2 times x low minus the error. Or 2 times x low. What's x low? X low is x minus the error. So it's 2 times x minus 2 times the error, and that's through 2 times x plus 2 times the error. So if we're trying to get our plus minus bounds, we get 2 times x, and it's plus or minus 2 times the error. So that basically brings up, error bounds and why this matters, and how you calculate simple error bound. Times x plus x low and x high plus y high will give us a new z low and z high, and we'll have our answer z plus or minus z error. And the z error is just going to be y error plus x error, right? We always add error. We never subtract error, right? We're never going to get more accurate measurements by adding inaccurate measurements. That's just not how science works. You can only increase your accuracy by increasing the accuracy of individual measurements. You can't increase your accuracies through mathematical equations, essentially. If you have garbage data, you're going to get garbage answers. Oh, they appear to all be broken a little bit. Huh, interesting. I'm definitely going to have to fix that after the stream. Don't want that causing any issues. Okay, so where were we before my desk collapsed on itself? We were calculating the... Oh no. Oh man, I might have to take a brief break, because this is actually going to cause the whole thing to snap off. So we will be back in just a moment after I fix my desk. Page I had about errors and uncertainty, we can see that this, instead of drawing, well, I'll draw it out in the notebook too. Why don't we do that? I'll prove it to you. Don't listen to these fools from college. Listen to me, because I'm clearly more educated. Anyway, if I zoom out, oh man, forgot to show the notebook. Well, what is missing? Well, I said that the error was 0.5 here, which is true, but not completely. That's 0.5 a roll. How many rolls are here? So that's looking better. But yeah, so now we have an error associated with our measurements, and we can say, that we know things now. You may have thought we knew things before, but now we know things for sure. And that's what's really important about science, is that you never get the right answer. The right answer will always elude you. You are never correct. You're only close. You're only ever close. And what's the most important thing you can do is to be able to measure how close you are and how close you can get. That way you can measure progress and see if you're getting closer or not. But once we get over this hoop of uncertainty, I swear, every time I tell you guys, next time we're going to do some more exploration. Well, I can't guarantee it next stream, but maybe 2 streams from now, after we've done some uncertainty stuff, we'll start doing some more exploring and, looking around the world that we're in, doing some more cataloging, that sort of thing, because that's also important. Not knowing what you're learning about is very difficult, right? You can learn all that there is about one subject, but if you don't know about just the general world that you live in, it's going to make life difficult, as you may find in this game. Anywho, I hope you all have a fantastic evening, filled with joy and all that jazz. I will see you next time.